You might have had to draw some in, I don't know. So we will redraw that first thing. Oh, this actually is a cool one. So this question is actually getting at kinetic and thermodynamic, which is going to increasingly keep appearing and appearing and appearing and appearing. So we got to watch out for it. So we've got a hydrogen, hydrogen there, and for contrast with blue, we have a hydrogen there. So we're now using T-butoxide, which I'm not going to draw that whole structure out, but we'll just say negative. Okay, and we now have to kind of process through how this reaction works. It just wanted the enolate. Oh, it just said remove the hydrogen, the correct hydrogen, and then draw your products, presumably.
You wanted the carbo anion and then the resonance structure.
Okay. So hopefully what we'd be able to see somewhat quickly, and if it's not somewhat quick, don't stress, is that we have two acidic hydrogens. There are a bunch of other hydrogens floating around, and I've lost my screen, so it'll come back hopefully in a second. There are a bunch of other hydrogens floating around in that structure, but really the only ones that are going to be particularly relevant are that black and that blue one. So you've got a hydrogen out here, 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 and here. Why are those purple hydrogens not particularly acidic while the black and blue ones are? Okay, so we could make an inductive argument. The distance is different. That inductive argument helps to explain why we should keep our focus on the black and blue as being more acidic, but there's a larger reason why the black and blue are now actually acidic, whereas the purple ones are not acidic. So induction is a great first step. Okay, the next part behind this would be acknowledging that you had resonance. So if we were to go through and have our base come through and remove that blue hydrogen, we'll draw this as a blue product. All those hydrogens are now confusing me. Electrons go to our carbon, and we would have that carbanion. Okay, if we consider the purple structures, we would have equally formed a carbanion, okay, a negative carbon. Why is this blue carbanion better than any of the purple potential products?
Their proximity to the oxygen.
Okay, proximity to the oxygen isn't necessarily a bad answer. That's where Addison went also. Okay, but we should be able to take it a step further because that proximity is ultimately just an argument of induction. Okay, and induction can be the answer, but it is also exceedingly rare to be the answer because where is induction on our list of reactivities? At the very, very bottom. Okay? So before we start using induction as an explanation, we should start evaluating all the other pieces. Okay? What are the other pieces? Where should we start?
Charge.
We should look at charge, size, electronegativity, resonance, and then induction. Okay. In those evaluations, what we're trying to compare is the whatever species we're looking at. So for the sake of comparison, if we did this with the purple structure, and I'm going to delete this structure in a little bit. Let's just remove the furthest hydrogen out there. We'd be comparing those two negative charges. So we'd start and say, well, is there a difference in charge? Well, no, they're both negative. We'd move to size. Well, what is the atom holding the charge? Carbon. In both cases, it's carbon, so there's not a difference in size because it's the same type of atom. We'd move to electronegativity. Electronegativity in this ranking is still an atom effect. Okay, these are both atom explanations. Since the atom itself is the same in both those cases, carbon and carbon, we don't care, so now we'd move on to a molecule effect. And we'd want to see either resonance or induction. Right? Resonance is how the electrons can move throughout the molecule. When we talked about atom size, we're talking about how the electrons can move throughout the atom. Right? So they're effectively the same principle. It's where can the electron exist in space, right? Either due to the size of the atom or due to how the electron's allowed to move, which is ultimately going to be resonance. So if we tried to now do resonance with both of these, again, ideally we're getting to a point now where we should be able to look and say with that purple one relatively quickly, there is no resonance option. I can't move the electrons into that to make a pi bond, because if I did, I would exceed the octet on that carbon. Okay? Exceeding the octet isn't necessarily a bad thing, but when I exceed the octet, I have to be able to move a pi bond if I'm going to do resonance. The only pi bond I would have would be the pi bond I just made, and I revert right back to the starting structure, effectively saying that there's no resonance. Right? If we move to the blue structure, what happens? I can move into that space, again, exceeding the octet on our carbon. Right? But it's not exceeding the octet that's the problem. It's exceeding the octet and not having a place to move electrons. So when we look at that exceeded octet, do I have a pi bond that I could move away from that problem? I do. So when I want to go through and discuss kind of the stability of these two systems, the purple one does not allow resonance, the blue one does allow resonance, because the blue one does allow resonance, okay, a stabilizing resonance. Okay, that makes the blue structure more stable than the red. And since the blue and purple structures, okay, since they are more stable, since the blue one is more stable, the reaction that formed it is more likely to occur. What was the reaction that formed it? It's an acid-base reaction. Okay, kind of makes sense? That's all we're trying to address. So in this case, we're saying that acid-base reaction is more likely. The purple structure then shouldn't be in my discussion for removing the hydrogens. And I can delete that from the system. Okay. Was the blue hydrogen the only one I had access to? I also could have gone from the black hydrogen. That black hydrogen is going to create a similar issue where I get a negative carbon. And again, I would ask, now the stability between black and blue, is there a difference? Well, I start with charge. They both have a negative charge. Size, the atom that's holding the charge, okay, it's an atom effect, is carbon, same size, same electronegativity. Do they have resonance? Yeah, the black one did have resonance. Okay, I could move those electrons inwards, exceeding the octet on that center carbon, which could then cause my electrons to move upwards. Okay, so both of these have resonance. You could say, well, what about induction? Well, they both pretty much have the same induction as well. So deciding between which of these two is going to happen becomes a much more challenging question, and I would argue that moves into what we could call category 6, which was the O crap or O carp, however you want to do it. And I wrote it as carp this time. Okay, which is, I really hoped I never had to address this difference. I don't want to look into the nuances behind that because there's all sorts of different things that can contribute to it, and that can become a mess. Okay? But we're now stuck in that category, potentially, for this system. Why potentially? Does the question allow me to put in two different answers? No. Okay, since it doesn't allow me to put in two different answers, I'm now stuck. I have to decide between these two. Okay, there is a third box. Okay, I drew curved arrows for it, so we might as well finish those out. Sorry for the silence as I draw. Okay, and we'd now be looking at either of those two pathways, and then we have to decide which is the correct pathway to put in. Okay? We could go through and kind of cheat and say once we've acknowledged two pathways, we could look at the answer that was already provided and be like, well, we know that answer was wrong, so therefore it must be the other pathway, and we just now change our answer. Problem with that is, why are you changing your answer? I think it's a simple question. Why? Why would we change our answer? So if we look at the pathway that was initially put in there, we're calling, what is that? That's the black pathway?
Doesn't matter when it's like a primary versus secondary.
Okay. Now what we're actually getting into is, how do we know which one should be correct? Our way to get the answer correct for the homework was we tried a 50-50, we were wrong, so we tried the other 50. Okay? That's not bad for navigating homework. That's incredibly bad for navigating an exam, because you won't find out you're wrong until it's too late. Okay? So how can we decide between black and blue which one's going to come through? So one option, we're in that O-carp category, and say, well, what about the stability of the negative? Okay, so when you're asking that question, which negative are you talking about?
The carboanion.
Okay, so if you're asking that question, there's this carboanion, right? So we could try and evaluate that. Okay, but isn't there also this oxyanion? And I would actually push this further. There's another negative we should be concerned about. The butoxide we started with. Okay? All three of those are things that we're now going to have to consider and decide where's the value, which one should we be evaluating as we navigate this. Okay, we're just trying to decide which one of these reactions is more successful. Okay? So before we get into deciding between that, could we look at narrowing the field between black and green? Which one of those structures do you think we should look at to help us think through whether that reaction was successful or not? It's a hard question.
We want to look at the black part, because that is what's dictating the outcome at the end.
So I would argue that what this black one is could be described with 4 letters. That's fun. Choose your 4 letters carefully. And I would argue the green one could be described with 6 letters.
Best and useful.
Best and useful. I flipped them, didn't I? I did. God damn
I
it.
think so, yes.
The black one can be described with 6 letters. And the green one could be described with 4 letters. That's what happens when you think on the fly. Okay, so we're talking about best versus useful. If we're looking at whether the reaction occurred, this step of the reaction, which one should we be looking at? The best structure or the useful structure? Okay, and that's a hard question. You should be looking at the best structure. The useful structure is very important. We want to look at the useful structure when we're talking about how that molecule reacts. I don't care how the molecule at this end reacts, because that's the next step. We're not talking about that. All we're talking about is this first step. And so when I'm looking at that first step, the one that I want to look at is the best structure. Okay? So the useful one is irrelevant. And I just realized I double used black. Apologize for that. All right? So can you tell me a difference between those best structures, between our green and black? Okay, we're seeing a change in where the pi bond is located. So we could potentially talk about more reactive, which again isn't necessarily bad, except if it's more reactive, what are you talking about? The next step. I don't care about the next step.
Pi bond
we could talk about its raw stability, and you're saying the stability is less stable at the end. But why? We can use at the end, but there's a better explanation. It's less substituted. We have a more substituted pi bond in blue than we have in the black. So what does that mean? If it's more substituted, what does that mean about the energy?
Slow.
It's lower. What's lower? The energy of the product. Okay. We talked about energies of products being lower and assigning a name with them. We're talking about a thermodynamic product. Okay. And then the other one, if this one's thermodynamic, this one might be kinetic. How would we know if it was kinetic? That's where we could potentially go back to the useful and talk about what hydrogens are being removed, where's accessibility, and all of those kind of things. Okay? And what we would indeed find is that we are talking about a kinetic product here. The hydrogen being removed in that space is more accessible, and therefore that reaction is going to happen faster. Because it happens faster, we're looking at a kinetic product. Okay? So how can we differentiate between our kinetic and our thermodynamic? I got to erase the whole reaction up top. And of course, I color-coded wrong again, but just deal with it. We'll call this one kinetic. So if I'm going to draw my thermodynamic on here as an energy diagram, how would I need to draw the thermodynamic? Cool. Higher activation barrier, cool, and lower energy product. If that was my energy diagram, what product do you think I get?
Kinetic first.
I will always get the kinetic first. That's not what I asked.
Okay.
It's a good question.
At that end, the kinetic.
The end of that reaction, which one do I get?
Thermo.
I get the thermodynamic. Why do I get the thermodynamic?
And it's irreversible.
Okay. Deciding becomes really challenging, so let's draw another energy diagram that would force a different output. This is still my kinetic. How do I draw my thermodynamic?
Bigger activation energy, and then at the bottom, be below the kinetic.
Okay. And I love how the emphasis in how you phrased that. It was kind of like, don't be an idiot, Mike. It's the same thing. Yes, because it is. It's exactly the same process. The thermodynamic is always going to have a higher activation barrier, and it's always going to be a lower energy product. That's how that difference happens. Okay. What product do I expect in this next reaction? We can call this B. We can call this A.
So wouldn't A have reversibility?
Talk at your tables. Talk to someone. Find someone nearby. Talk to them. For each of those reactions, which one do you think is the product?
A has reversibility, and therefore the thermodynamic, or
Because
the outcome.
activation,
I guess it just.
While B
the kinetic
can't really be reversed.
for A, the kinetic seems really reversible, but for B, the kinetic is not very reversible. So we might get more kinetic product in B.
Where does it say reversible?
The activation energy in the opposite direction.
Do you guys understand what she just said? Okay, just checking.
So I think in A we'll end up getting, I think it's the reversibility that makes it. Yeah.
What do you guys have? Okay. So we could look at higher activation energy. Are they really that different? I tried to make that as close as possible. But I would argue the activation energy isn't that different. Do you see any other difference? What do you mean?
Like the change in G between this and the reaction.
Change in G.
It's higher in B than it is
Let's just look at the kinetic one.
So,
It's going to be real hard for me to even draw an arrow for that one, right? What does that mean? So, to your question, that's the difference. It's where the product energy is relative to the reactant energy, which we would call delta G. This is pulling up all the dredges of nastiness from 152, okay, and trying to manipulate that system. What does that mean for us? In both cases, we could say, well, the kinetic is always going to happen, right? The only reason we would ever get the thermodynamic is something has to change within this, right? Because the kinetic will always happen first. But if we look at this first one, the reverse activation energy, let's call that 1. If we look at it in the other case, what's that reverse activation energy? Is that also 1? We can call that 2. Okay. So what does that mean about the reactions, the kinetic product's ability to revert back to starting material? Reaction A, much easier. Reaction B, that's not going to happen. Okay. It is that reversibility that's causing us to oscillate between one product versus the other. Kind of makes sense? Which I still didn't finish the thought. But there's our difference, and that's what we should be considering. Yes, they're both alpha hydrogens. So you guys are using some fancy words, so we'll have you guys talk through it. So what do you...
Sorry. Sorry, I'm looking at the smart word, but I'm looking at my question one.
Anybody else at the table want to talk through it? No? Okay. So let's go back to this now that we had some time to kind of address it. So a couple questions came out. Is number one, what's the difference? What is the difference between reaction A and reaction B? I don't see that. Okay? And there's a lot of different things that you could try and key in on and reference. Okay? There was at first a statement, well, the transition state is at a different energy level. I tried to make that about the same for both officially, subconsciously. I don't think I actually attempted to do that, but that's what I was trying to do. Okay? Make sure that that spot was relatively the same. So that when we look at the forward reaction, the activation energy for the forward reaction in both of these systems is about the same. Okay? So where is the difference then? Well, the difference comes in the product energy. And in particular, the product energy relative to the reactant. That's our big difference. Okay? And if we look at reaction B, well, let's take a step back from that first. Either scenario, the product we get first is the kinetic, period, always. Okay? And so if we went through back to our original question and said, oh, it's the kinetic, we were wrong. Right? Well, why is that? Okay? Because there's something else going on, and that's where understanding the energy diagrams can kind of help us manipulate this to a certain extent, or you start to memorize certain things about reagents. So if we look at those two differences, let's look at that kinetic. The kinetic energy is really the only one I care about. Okay, if I look at the reverse reaction, it has an EA listed in red, okay, or an EA listed in red for the first reaction, or for A and B. For B, it's twice as high. What does that mean about the reaction's ability to reverse? It is less likely to reverse. So if we're looking at our reaction system, we produce kinetic product. Ta-da, done. But reaction A has a higher propensity to reverse, meaning it's in equilibrium, which means I form the product and I go back to form reactant. Well, if the kinetic always forms first, how would I ever get thermodynamic? Okay? This is where we could start to bring in other things that we brought in earlier. We could say, well, we had higher temperature, or you just have more time. Okay? You will always produce a little bit of both, period. Okay? The question becomes, is which one are you trying to favor? So in reaction A, we do an equilibrium back and forth between reactant and the kinetic product. Some of that reactant turns to thermodynamic. And note, what's the big difference in how I've drawn that for reaction A? The thermodynamic one is unidirectional. It is only going to make thermodynamic product. Okay? It's not why is it not in equilibrium?
The reverse activation energy is so much higher for thermodynamic.
Its relative activation energy is so much larger than it is for the kinetic that is effectively a unidirectional reaction. And if we go through and look at reaction B, what happens? Okay, well, we still get our reactant and our thermodynamic, kinetic and thermodynamic products being formed, except the kinetic product is now not in equilibrium. And if it's not in equilibrium, since it forms the fastest, I get the kinetic product. I'll still get some thermodynamic, but it's going to be a relatively small amount. And so the only thing I get in reaction B is kinetic. In reaction A, I start to build up a larger surplus of the thermodynamic. Why? Well, Le Chatelier's principle. R to kinetic, we get an oscillation between them, but then that R is constantly siphoned out to make our thermodynamic product. And according to Le Chatelier, what does Le Chatelier try to do? Fix the stressor by converting that kinetic product back into the reactant. The thermodynamic comes through, swaps that reactant out, and so we constantly siphon the kinetic product out into the thermodynamic product. Under conditions B, we never get that. There is no equilibrium there. And so this is where we bring in the concept of reversible and irreversible. What we're talking about is the formation of your kinetic product. Is that a reversible or irreversible step? And there's varying things we can do to tweak that. Earlier on, we did temperature. Okay, that was really all we could say. Oh, we changed the temperature. You change the temperature, you can increase the energy, so allowing for the reverse reaction to happen. Okay? We also had to provide lots and lots of time because we had to deal with that first equilibrium and then siphon it off to make the thermodynamic. Because you're always making a relatively small amount of the thermodynamic product. Kind of make sense? So when we now go back to our reactions here, we're trying to decide which curve correctly represents this reaction. Is it curve A, in which case I would expect the thermodynamic product, or is it curve B, in which case I get the kinetic? Well, how do I decide that? It's all about the relative energy between reactant and product. That's what started the whole cascade. So what I want to be able to go through and do is look at my chemical reaction that looks like a giant clusterfuck right now. Okay, but we'll clean it up a little bit. I'll delete some stuff. And we want to decide what is the relative energy between my reactant and my product. Can I'm not sure how much I can clean this up. We're going to get rid of all this. Because I don't want that. Okay. In relative energy, do I want to be looking at my useful structure or my best structure for my product? I want my best. I don't care where it goes. That's my useful. I care where it ends. Where it ends is with my best. So I'm going to be looking at my best structures. So I want to compare my best structures as my products to my reactants so that I can figure out where they are relative to each other, right? So what thing am I looking at in my reactants to define that starting well? Okay? I've got two structures. I've got this giant red structure with all the hydrogens on it. Right? Well, that's what we reacted, so that's what we should look at. No. Because when we're trying to go through and dictate chemical reactions and what things are going to react, where do we start looking? Well, I don't remember. Rewind the video when you get home about, I talk forever, 15 minutes, 20 minutes. Where are we at? That's probably 15 minutes. And we wrote up a list of where we started looking at things. That list started with number 1, charge. Do I have a difference in charge between my hydrogen structure and the other reagent? Yes. That's where I'm going to start my energetics. This charge structure is what's dictating the chemistry of the entire frickin' reaction. That's where I'm going to start my conversation. So now I'm going to compare the reactivity of that negative charge to my useful products. And I want to compare them. Well, how do I compare them? Where should I start that comparison? With the charge. Okay? So what was the charge in my reactant? We'll use green. It was a negative oxygen. What is the charge in my product?
Negative.
It's a negative oxygen. So is the charge different? No. So what's the next thing on my list? Size. The atom that holds the charge, the reactive species, is oxygen and oxygen. Is there a difference in size between oxygens? No. What's the next thing? Electronegativity. Okay, same element. Not much difference. Resonance. We're now starting to see some resonance. Okay, so we could see that this potential product is maybe a little bit more stable than where we started. Okay, because we're starting to pick up resonance in that argument. Is that enough to cause a shift? That question is the hard question. How much different does it have to be to cause that energy differential? This is establishing what is referenced in some of the lectures, the line in reactivity, when I switch from one reactive site to a different reactive site. Where's that line? Okay? Negative oxygen versus negative oxygen, there is not very much difference. And if there's not much difference in stability, which curve am I looking at? A or B? We're looking at A. The difference between my reactant and my product are effectively the same. And if I'm looking at A, I'm going to form the kinetic first, but that reaction is reversible. Which then means I get all the thermodynamic product. Everything siphons into the thermodynamic. Which then means between these two answers where I'm like, I like the black structure best, and that's the one I drew, and I was wrong, the blue structure had to be right. Why was it right? It was right all the way back here when we wrote out T-but-ox, or the T-but-O-. That dictated where the whole thing went. So I have to be able to look at that base and very quickly decide, should this be going reversible or irreversible? And there are ways to go through and do that. We just walked through one. We don't know, so we draw it all out and we think through that whole process. That took us 33 minutes. What's the other process? Memorize. What are you memorizing? Can I clear everything? I said the only thing that mattered in determining this was looking at that T-but-ox and classifying that reagent in a particular category. In the particular category we looked at, that base allowed for the reversibility of that acid-base reaction. It was reversible, so we could call that a reversible base. The reversible base resulted in, I screwed up the color coding. No, I didn't. I did it right. Resulted in which product? The thermodynamic. So I would want to be able to go through and say, well, what would make thing a kinetic product or a kinetic base? Well, the kinetic base should be irreversible. I don't know why I changed capitalization. Deal with it. When we looked at our chemical reaction, we had our base with a charge, and then what we ended with was our enolate. To make something irreversible, what does that mean has to be true in this reaction? there has to be a difference in energy between our base and our oxygen. Okay? And this is where we could introduce other goofy-ass terms that I brought into the lectures. Okay? How about hydroxide? Hydroxide is what kind of a base? A strong base. So we say, oh, if it's a strong base, that should be irreversible, right? Except what are we comparing that hydroxide to? The negative oxygen. Is there a difference there? No, which means that's reversible. How can I get an irreversible base? Okay. It needs to be stronger. So I need to pick something else that would cause my base to be stronger than a strong base. Okay? Which is why in the lectures I go through and call it stupid strong. Okay? Because it has to be stronger. So how could I make hydroxide a stronger base? What does a base need to do? Two definitions, only one is useful here. Take hydrogens, not useful. How does it take hydrogens? By donating electrons. So for it to become a stronger base, it must be more able to donate the electrons. Why is oxygen less able to donate electrons? It's very okay. If it's less electronegative, what could we do? Or very electronegative, what could we do to make it something more able to donate electrons? Make it less electronegative. How about we use nitrogen? Nitrogen being less electronegative than the oxygen, okay, doesn't hold the electrons as well, so it is now more basic. If I now compare negative nitrogen to negative oxygen, which one's more stable? The oxygen, which means that reaction is irreversible. Okay. What are other things that affect base strength other than electronegativity? The size. You mean we could go back to charge, size, electronegativity? Yeah, you just go back and you just start where you're at. We're looking at electronegativity as the easiest one. So size. Oxygen is pretty small. Is there anything smaller than oxygen?
Hydrogen.
Say again?
Hydrogen.
Hydrogen. Within the row, remember, first approximation, they're all the same size, so we'd have to go to a higher row. We've never seen helium react, so it's got to be hydrogen. So what if I made H minus?
That's really reactive.
That's insanely reactive. That would be an irreversible base. Okay? So let's try another one. Let's not give anything away. Let's go with... Let's go with that structure. We could be really annoying. Let's do this. Reversible or irreversible? What part does that not look like an L?
It looks like a lone pair.
It looks like lone pairs and
Man, did not realize how quickly I was going to get shot down on that one. Wow. Okay. So we're going to have a conversation with this side of the classroom now. You all are a little nicer. Where should we classify this one?
Irreversible.
What's that?
Irreversible.
Why?
The nitrogen.
Oh, but I've got all these carbons.
Okay.
I kind of liked your emphasis in that too. Are those carbons doing anything? Where's the chemistry? All right, and this is where I want you to be real careful. Where's the chemistry in this molecule?
The lithium's going to leave, and the nitrogen's going to accept the negative.
I don't like your word choice, but yes, I'm with you. The lithium doesn't leave, because if it leaves, what does that mean? It takes the electrons with it. So the lithium falls off, however you want to reference that. Okay? And the primary reason, because we want those electrons to be left behind. What we're looking at there is an ionic bond.
Because it's in the same column as sodium, so they're both like pretty equally electronegative.
We can try that. It's easier than that. How do we know this is an ionic bond? Lithium is a metal. Okay? I don't even need to deal with, it's reactivity with sodium. That's a conversation for a different section. Okay? But that's an ionic bond, which means lithium becomes positive, the nitrogen becomes negative. What's the reactivity? It's a negative nitrogen. Well, what about those carbons? I don't care. Okay? We could draw. Maybe this side of the classroom will be nicer for me than the other side of the classroom. Well, what if there's a pineapple connected to it? I don't think it's stupid. It's still the negative nitrogen. That's a pretty dang good pineapple. It's the negative nitrogen. That's the thing that drives the chemistry. That's what my primary focus. Only after the fact that if I can't differentiate by looking at that charged species, now I can start to say, does the molecule have some larger effect? Okay? Don't make it harder by getting lost in the stupid drawings that I'm putting up there. Focus where the charge is. Focus where your reactivity is. Okay? That species is known as L for lithium diisopropyl amide. Whoa. Even I can admit. That one I just fully screwed up. But that's LDA. So you'll see LDA written all over the place. Okay? Are you responsible for knowing what LDA is? Yeah, kinda, yeah. That is one that I would draw up if you asked on an exam and I didn't give you the structure right away. I'd be like, you should know that. I'm sorry, you should really know that, but I'm going to draw it up. Okay? And that you should know that is probably why I will try to not say it, because it's full on a judgment. If you don't know what LDA is by the time the exam rolls around, you're probably not prepared for the exam. Okay? So I do try to limit those kind of statements during the exam and just, yeah, sure, let me draw the structure for you. Does that make sense? Okay. Are all oxide bases going to be thermodynamic? Let's just go with yes. It's a pretty absolute, which makes me really nervous, but I'm just going to say yes. Does that make sense? Okay. Which then means now we know why it was one product versus the other, right, in our drawing. Okay. How did you do it? Did you recognize they were both, just drew it, and then you're like, it must be the other one?
Yes.
Okay. Which, again, homework is fine. Okay. That's perfectly acceptable.
Actually, I was thinking something about the base, however, not what we just concluded. I was thinking, that base looks a little bigger, so it's probably a thing.
And that's, full disclosure would admit, is a very challenging part behind this, because you start to think about sterics, and unfortunately sterics has very little to do with this.
Okay.
It's going to be the energetics between those. Fine to do that in the homework, but when it comes to class, you should be like, why should it be changed? Which I would argue in this case, a little bit of coaxing from colleagues. Andrew's called us up and said, okay, why? That's perfect. That's what you should be doing. And if you don't want to do it in class, because I took half an hour to answer 45 minutes to answer one question, then do it in office hours. Okay? Do it in email. Okay? Last part, why can't I read? Describe the reaction and or describe all. Oh, this is just a nomenclature question at this point. So they're just having you go through and do you recognize all the words that are associated with this? I care less about this What I would care about is that overall reaction. Since it's a grouped question, you may not actually see that second part in your questions. You are technically responsible for how things are phrased, particularly as it comes to the ACS. Okay, so I want you to see those terms. You can ask about them if, like, during the test, you're like, what's a beta deprotonation? I honestly, I don't know how I would answer that question to describe it to you in a way that didn't give away answers. Okay, where I would probably go is beta is a labeling system. What chemical reaction would allow you to remove a hydrogen from the beta position?
So it's like the black hydrogen versus the blue hydrogen.
So beta is a locator, and this is one of the reasons why I don't like this labeling. So number one, sorry, got it wrong. Okay, where is the beta position? We'll draw this one out. Where's my beta carbon? That's my beta carbon. So this is my functional group. It is connected to the alpha carbons. The next one would be beta, alpha, beta, delta. Is it gamma, delta?
I think just gamma is next.
Okay, yeah. Always got time for that. Okay. So where have you seen beta deprotonations happen? There's my functional group, which means this next carbon is alpha. Beta, if I remove that beta hydrogen, so base comes along, removes the hydrogen, we typically wouldn't call it a beta deprotonation, we'd call it a beta elimination. Okay, so that's where that terminology came in. We are going to keep hearing alpha and beta referenced. Okay, even calling it an alpha deprotonation I think is weird. But it is technically an alpha deprotonation. Kind of makes sense? Next.
We should do the last one.
Okay.
I mean,
So what do you end up seeing? What's the reactivity pieces that you see coming out of this?
The nitrogen is the reactive part of the reagent.
Why is the nitrogen reactive? Okay, so the reactivity that you're seeing is we have a lone pair on that nitrogen, which means that nitrogen could act as base or a nucleophile. Awesome. Okay. And I'm okay with that, though technically I would say you should have seen something else as more reactive first.
Is it the hydroxide?
Okay. Ideally, we would have zeroed in on the NaOH as our reactive thing first, okay, which is a bit misleading, but that's an ionic bond. We have the sodium and then we have the negative oxygen. So we could ignore our sodium and just go with the hydroxide. Okay, and it's misleading. Why is it misleading to look at the hydroxide first?
Because it's underneath the excess.
Nah, I would argue that's not relevant.
because it's saying
Then. It's that then, which is really saying that the sodium hydroxide is a step 2. Right? So if we're going to talk about the reactivity, I need to ignore the hydroxide first and consider what else is going on within this system. Okay, so in our step 1, we've got the nitrogen, which could act as a nucleophile or a base, and then we have that CH3Br. Where's the reactivity we see within the CH3Br? Say that again? Br is a leaving group. I'm going to redraw that. We could see the lone pairs, all of the bromide, but we have to realize those lone pairs are not nucleophilic until after it has left. So we have bromide as a good leaving group, but that would leave behind what kind of carbocation? A primary, or this is a step lower than that actually, because there's no carbons connected to it. We've got a 0 area carbon. That's not going to be great. Okay? So it's not going to leave on its own. Something would have to force it off. What kind of thing could force that bromine off? Well, we're talking about bromine leaving with the electrons, which means the thing to force it off must supply electrons. What else should we note within our drawing? The nitrogen has now lost its lone pair. It's now positively charged. We have the bromide chilling around. The bromide in and of itself is not going to be particularly reactive because it's stable. Large, electronegative, not particularly relevant. Which then means we can move to our then, and we're now introducing hydroxide. What could hydroxide act as? A base or nucleophile. So we get both those options. Do we see anything screaming acidic? Okay, so I would argue for those people being like, no, I would agree. I don't see anything that's screaming acidic at me. Okay, which could mean nucleophile. Okay, so if we're doing a nucleophile, it would need to attack an electrophile, and that electrophile would be electrophilic because. And what? Okay, so cool, it's positive. So we would have this electrons come in and attack the nitrogen. Okay, so I heard a couple things. Oh, it's got too many bonds. Okay, but when we ran a substitution reaction, we had too many bonds too, right? Okay, we put a bromine, we can take our hydroxide. Kicks that off, right? Ignore that it looks ugly. Okay, so we could do that. What is different about my black drawing from the colorful one?
Focusing on the reagents with the arrow, you're not focusing on the end.
We don't even care about the arrow anymore, just this reaction. My colorful reaction here versus the one in black. There's a couple big difference I would go with.
Hydroxide is reacting somewhere else.
Hydroxide's reacting at the positive site. Hydroxide's reacting at the positive site. I would argue those are exactly the same. Okay, there's an interesting difference. We're looking at the oxygen reacting with a nitrogen versus a carbon, but are both of them positive? Yeah. We don't like things attacking the nitrogen, and we'll come back to why that is in a second.
The black one has a leaving group. And
Okay, so I would argue we have a second arrow in that black structure. That second arrow is that we have a leaving group. If we have our oxygen come in and attack the nitrogen, what would our leaving group be?
The CH3?
Okay, a CH3. Sure, let's do that. What would our product be? That big, ugly nitrogen oxygen structure and a negative CH3. Do we like negative CH3s? No. So that didn't happen. So what else could leave? Any of the other carbons. Any of them. And all of those would result in negative carbons. Are negative carbons good leaving groups? No. Okay? So when we're looking at reactivity, it's not just bring positive to negative. Okay, so we're going to delete this one and we'll draw out another classic reaction. H3O plus. How does that react? Because people, I can already see making faces about my 3. H3O plus, how does that react? You spent at least a year studying this. It donates a hydrogen. This is an acid. It gives you H+, right? Draw out the Lewis structure. It's got a positive charge. Where's the positive charge? But you said hydrogen was the one that's reactive. Okay? If you change your it, you could actually get a potential for it leaves being correct. What leaves? It's not the hydrogen that leaves.
It's the oxygen.
The oxygen that leaves. Okay? So we're looking at the oxygen taking the electrons away from the hydrogen. Okay? So if we go back up to this reaction, yes, we have the nitrogen here. Do we have a good leaving group connected to it?
Of course.
There was no good leaving group, which means it's not the thing being attacked. What is it acting as? It's acting as the leaving group. That's it. You're like, but I've never seen it do that. Well, I know. That's why we're talking about it now. Of course you haven't seen it. Make it look like something you have seen. All it is a leaving group. This is a tricky leaving group because when we look at H3O+, if we said the water was acting as our leaving group, how many leaving group options do we have? 1. How many leaving group options do we have with the nitrogen structure? There are 3 different places, arguably 4 different places it could leave from. How do we decide which of those places? That becomes the crux of this question and how you would navigate it. So it is going to pick up some content that you have to know to be able to address this. Okay? So we could look at it attacking up here, the nitrogen leaves. Attacking here, nitrogen leaves. Attacking here, nitrogen leaves. We'll go black. Attacking here, nitrogen leaves. Do not draw any of that, please. Okay? What chemical reaction did we just show happen? Substitution. Okay? That's hard. You're predicting what the product would look like. But yeah, that's a substitution reaction. Okay? What evidence tells you that this should be a substitution reaction? We've got a strong nucleophile, right, with a negative oxygen.
Ooh, we got some heat going on.
Ooh, okay. So strong nucleophiles could also be strong bases. Can't hydroxide also act as a base? Yes. Which means we're now right back in Gen Chem, OChem 1, deciding, am I elimination or am I substitution? Okay. How would we go through and decide that? Well, how did we decide it in OChem 1?
We looked at all the factors.
We looked at all the factors. What other factors should we be looking at? Yeah, we go all the way back to our reaction, and there was that nice little delta symbol, that delta symbol representing heat. And heat was a red flag for elimination. Okay, so all those arrows I drew, which is why I told you not to draw them, were wrong, because those were all running substitution. We needed to do an elimination. Okay, so we would have to run the elimination. We have to remove a hydrogen. A hydrogen from where? Beta to the leaving group. Where was our leaving group? The nitrogen, which means this is alpha. Do I have a beta up? No. This is alpha. Do I have a beta? Yes. This is alpha. There's 2 betas. Are there 2 betas?
No, because they're identical.
Okay. So yes, there's 2 sites that are beta to that green alpha, but both of those sites are equivalent, so it doesn't really matter. We're going to get the same product whichever one we attack.
And it's the same thing with the carbon on the other side.
Cool. Okay. We could say alpha and beta out that side, which is the same as the purple one. So we've now simplified this down. We don't have to worry about that initial alpha I drew on. And really all we're looking at is a purple path versus a green path for this elimination. We're talking about removing the hydrogen here, or we're removing the hydrogen here. What products would we get if we did those eliminations? Okay, and everybody struggles with like seeing this and visualizing it, right? And one of the common things that came up is, I don't know how the rings are reacting. Are the rings reacting? No. The only thing that's reacting is at the alpha and beta positions. I don't care that there's rings. That's 100% irrelevant to the conversation. Focus at where the chemistry is, draw the result that would come out of it. And I would argue you should draw the result, right? And so I'm going to go through and draw one. So our base comes in, attacks our hydrogen. And Drew laughed. I wonder why he laughed. I suspect I know why. Removes the hydrogen. The electrons swing in to make the pi bond, and I kick out the leaving group. So if I'm going to draw this, there's my alpha, there's my beta. Between the alpha and the beta, I know I have a double bond now. That beta goes up to the right to a carbon that I had labeled as my purple beta. Then it goes up, then it goes there, encounters a nitrogen. The connection between the nitrogen and my alpha is no longer present, so I don't want that there. I should probably remember that I've got something underneath it. Okay, and I draw out the rest of my structure. That's my answer. I didn't say it was the answer for those people hemming and hawing. Okay, I guess officially I should drop the lone pair on that nitrogen. Okay, and we now have that structure. Everybody see the process by which that was drawn, because that's the focal point behind this. Don't worry about the rings. We didn't start with the rings. We drew where the chemistry happened, and then we just connected the rest of the things around it as necessary. Kind of makes sense? Okay. You guys want to try and do the purple one on your own, because we got enough time? Think you can draw it? Okay. I'll give you a minute or two. You're redrawing it, making it look pretty, but yeah. So, if we're going to have it react with the purple one, we're taking our electrons. They pull off the hydrogen. That means the electrons between the carbon and the hydrogen have to go somewhere because we've exceeded the octet on the hydrogen. So where do we move those electrons? Before we get too excited about answering that, I just want to walk through the wrong thing. If we shuttle our electrons over here, what we're now saying is we want to build a pi bond between those two carbons. That means we're going to exceed the octet, right? Do we have a leaving group at that carbon? No. And if there's no leaving group, what does that mean about that arrow? I'll take that to mean it's wrong. Okay, so what we would backtrack through and say, well, where else could we move those electrons? We could move them here. Okay. Do we have a leaving group at the alpha position? At our purple alpha? Yeah, we have the nitrogen, so we could shuttle the electrons towards the nitrogen. Okay, so what happens? So nitrogen, I'll draw out the left structure. Nothing changed with those, so I'm going to leave those alone. Okay, and then depending on what you find easier, for me, I would probably find it easier to make sure the nitrogen has its lone pair, make sure I don't forget that CH3. Okay, and then try and process the rest. Okay, this has to go up to another carbon. Okay, and if I look at it, this was my alpha, this is my beta. I moved electrons in to make a pi bond between my alpha and my beta, and I have that. So I now get two potential answers for this elimination reaction. I get my green answer or my purple answer. How would we know which one happens? Okay. The argument that we would do for all elimination reactions goes back to stability. So we could say which of those pi bonds is more stable. The green one is more stable, so we would say the green one is our answer. Okay. What you just described was the Zaitsev's product, okay, which is perfectly legit for an elimination reaction. That makes a lot of sense. However, nitrogen just wants to screw you over, and no. You don't get the Zaitsev product. Okay, you get the purple one. Okay, this is unanticipated because you're getting the less substituted double bond. You're getting the thing that is more reactive. That makes no physical sense. Why would it ever do that? Well, of course, since it makes no physical sense, what do? We could talk about chemical sense and how that works. You name it. It picks up a named reaction. Okay? Zaitsev, I would argue, shouldn't even be used as a name because you're just following stability, you're following chemistry. It makes sense. Because it makes sense, there's no reason to name it after anybody because it makes sense. Okay? This one doesn't make sense. I fully accept, yes, we should go through and name this. This is what's known as the Hoffman elimination. The Hoffman elimination is forming the less substituted double bond. Okay? Because it doesn't make sense, I would argue it's something that's worthwhile memorizing because you're not going to be able to reason through why it happens easily. Okay? Because technically you can reason through it. Okay? But to reason through it, you got to bring in somebody else's name. There's another name we have to invoke. Newman. To see why we get the Hoffman product, you actually have to draw Newman projections for both reactions. And when you go through and look at the Newman projections, this nitrogen as a leaving group is so bulky and nasty that it prevents the Zaitsev elimination. And only the Hoffman is allowed. How many of you want to draw Newman projections for every single elimination on a test?
Absolutely.
Okay, memorize it as the Hoffman so that you know that context and you now don't have to worry about dealing with Newman projections. But the Newman projections do allow you to see it, okay, which I think is awesome and fantastic. The textbook does a good job showing it for an example. So if you want to look at those pictures, Cardi did a good job drawing out all those Newman projections so you could see that. I think it's cool, not worth the trouble for probably the majority of you. Ain't nobody's got time for chemistry.
Wouldn't it be enough to look at that and say an 8-member ring is a lot less stable than
No.
the ring? No?
So, we've got it named, but why is it like a Hoffman elimination in this case? Do we need to, like, is there another explanation for why?
The Y requires that you go in and look at the Newman projections for both this green reaction and the purple reaction. And what you'll see within the Newman projections is the purple reaction is a direct result of stable Newman projections. The green product is a result only of unstable Newman projections.
Because of like eclipsed
Yep.
substituents?
Yep. It's how your substituents, I don't think it's fully eclipsed, but you're looking at Gaussian green and anti and purple.
Can you show us what it looks like?
The Newman projection, I'm just trying to visualize it.
Like what a Newman projection is?
No, I know what that is, but like with this actual shape, so it has to be.
So for the record, it is 12:51, so we're going to go ahead and stop class.